No problem.
Okay, thank you.
So yeah, my project here was on direct conversion, which is the process of down converting radio signals to audio signals. So basically, I wanted to build a radio transceiver system that could actually pull some 7 megahertz signals out of the air. So why would you want to use 7 megahertz? Like what's special about 7 megahertz? Well, 7 megahertz is in a range of radio frequencies that people kind of call the shortwave bands, or sometimes the HF bands. Basically, there's this weird phenomena where solar winds come in off the sun and ionize the upper layer of air in the atmosphere. Basically creates a layer of charged particles. And radio frequencies at 7 megahertz can actually travel off the surface of the Earth, reflect off that charged layer of charged particles, and come back towards the Earth, allowing for radio reception with very large distances and little power. So it's very convenient. Amateur radio operators commonly use this band for Morse code, which is good for us. This is what my transceiver mainly deals with. There are other modes like voice and whatnot, but primarily for this project, just did Morse code. So this is a block diagram of a direct conversion receiver where, as I stated previously, RF signals are just being down converted directly to audio, to sound. The circuitry is fairly simplistic and works well at low frequencies. It's a little tricky when you get above about 30 megahertz, but it does work up to about that range. And it was a technique that was originally used in the electronic musical instrument developed by Leon Theremin in 1925. When he created the theremin, it's basically the same setup as this block diagram. Only instead of an antenna to get signals out of the air, he used another oscillator. So you have 2 oscillators that are around the same frequency that are producing this audio tone. They are RF signals, though. They are 270 kilohertz, well beyond anything we can hear. But using this technique, he made a musical instrument out of it. Somewhere in the 1930s, it got adapted by the British Navy, supposedly, and they started using it as a radio communications device, but pretty much died out until the 60s when Wes Hayward wrote an article for QST talking about how he was able to use it with amateur radio. Down converting is a strange process, and it's a little more difficult than just tuning in a radio station like we normally do. Incoming RF signals off the antenna produce an audio tone when they're both above and below the frequency that we are tuned to. So it's that frequency offset that allows us to hear the other station. If the local oscillator and the incoming signal are right at the same frequency, the difference between that is 0. So we don't hear any signal at all. And this is what they call zero beating sometimes. But yeah, when we're transmitting, if we're receiving and trying to transmit on the same frequency as the station we're receiving, we need to be able to switch back and forth between those 2 frequencies kind of dependently in order for us to be able to hear each other. So it's kind of a strange process, even in the radio world. So we can receive an audio tone, but we want to be able to talk to that station. We want to be able to generate an audio tone on their side so that we can use Morse code to talk to one another. So basically here I've taken the receiver and added another section for the transmitter. And what will happen is we'll have a little microcontroller that will take contact from a switch and switch between these 2 functions of receive and transmit. So I've got to design some RF switches that'll be able to actually respond to this control signal being sent by the microcontroller. The research objectives for this were mainly to design a 7 megahertz direct conversion transceiver, mainly for portable use, so I could carry it out backpacking or in the woods or wherever I may be. And with that criteria, we wanted to be able to generate enough power better than, but at least a watt. A watt of RF energy is quite a lot of energy, even though if you think of a 1 watt light bulb, it's probably not very bright. But it, in this case, is enough to travel thousands of miles away from the transmitting source. So it's good for portable use. We also want to be able to receive signals down to negative 120 dBm. That means that the receiver has to receive signals as weak as 1/quadrillionth of a watt. That's 10 to the 15. It's a very tiny amount of energy. You can, if you need a way to imagine how much energy that is, that's about the same amount of energy as a snowflake striking the ground. So really tiny, and quite a big difference between transmit and receive. Also want to use a microcontroller for the transmit receive switching and determine if adequate RF performance can be actually achieved with modern digital circuitry. So here is a block diagram. We'll go over some of the design, the way I designed the sections of the receiver section. There's basically a low pass filter, a low noise amplifier, and this product mixer. This is the local oscillator that also comes up into the product mixer. And out of this port, we get the sum and the difference of these two signals. So that's our audio frequency. Then we'll have to amplify that with a little audio amplifier into a speaker so we can actually hear the tone that we're looking to hear. So this was the diode ring mixer. It's basically just a small ring of diodes that produce the product of two input signals. So if we put in one signal on the LO port over here, put in another signal on the RF port, out of the IF port or the intermediate frequency port, we actually get the product of the two signals. The product of the two signals is the sum and the difference. So we'll mainly focus on the difference being the audio. So this is chose to do use an ADE1 little surface mount diode ring mixer. So I didn't have to build any of this stuff. It was all contained in that single package. I did have to design the local oscillator, and an oscillator is basically just any amplifier with a positive feedback circuit and a gain greater than unity, or a gain greater than 1. So we can achieve oscillation just by adding this feedback path and making sure that this transistor is biased so that we actually get a little bit of gain. The input signal is a little bit greater than its output signal. Additionally, quartz has a crystalline atomic structure that we can actually cut to resonate at a specific frequency. So we can use this. This is a model of a crystal resonator over here, but if I put this in line, we can force this oscillation frequency to oscillate at the frequency that this crystal is cut for. So a really fascinating use of quartz crystals. Additionally, I guess the problem of using quartz is that it wants to really just oscillate at the single frequency that it's cut for. So in order to be able to tune our radio up and down the band, we need to be able to pull the frequency from the one that it's designed for. So we can add these external elements, this little inductor and capacitor ground, and as we change this capacitance, we'll actually tune the frequency. So we'll get to design that, play around with that a little bit. Then we can also design some passive low-pass filters to help us also select the station we want to hear and not just listen to all of them all at the same time, which is a little nauseating. So basically, to design these, all I had to do was choose a characteristic impedance of 50 ohms and use these kind of scalable prototypes to achieve the values of capacitors and inductors that I needed at a specific frequency. You can do this for radio, you can do it for audio, and you don't need anything other than some capacitors and some coils of wire to make really, really good filters. We also needed a low noise amplifier to improve the reception of really weak signals that are coming into the antenna, get us down to that negative 120 dBm range. So I chose to do this single tuned audio amplifier, or sorry, single tuned, just a low noise amplifier in order to be able to pick up those RF signals. Signals on the AM broadcast band can be really strong and overwhelm the receiver. So I had to design some sort of ability to attenuate those signals a little bit. And then an audio amplifier design. The audio amplifier is basically 2 stages. So we can just use a single op amp, in this case an NE 5532. One stage provides the voltage gain. There's a mute button there. And then there's another op amp here to drive this complementary symmetry stage. So this bias network here allows us to manage the power dissipation between these 2 transistors, and that helps reduce the wasted current to ground and not draining off our battery life. I also put a couple caps here in the feedback network just to provide added filtering for any signals coming off the product mixer. Now, I want to be able to talk back to the station I'm listening to, so I might want to design a transmitter of some kind. So in this case, I just had the local oscillator switching into a power amplifier. So we had to do a little bit of a power amplifier design. You can't talk much about power amplifiers without mentioning efficiency. And this transceiver, it's for portable use. It's running on battery power, so it's a big important factor to consider. Basically, all these schemes of achieving efficiency in a power amplifier come by exploiting something called the conduction angle. The conduction angle is the portion of the input signal where the amplifier is conducting current. So it's actually dissipating power over some portion of the signal. Class A is where it's just conducting the whole time the input signal's there. B and C kind of take advantage of this reduced conduction angle to get greater efficiency. The only problem is that these conduction angles, when you do that, you sacrifice gain, so you don't get as much power out in that case. So my solution to this was to just develop 2 stages. The first stage would be like a class A using a BS170 MOSFET. Class A amplifier has a theoretical maximum efficiency of 50%, but my hopes was that this would be enough to drive the next stage, the final amplifier stage, where we could actually take advantage of these sort of higher efficiency schemes in order to reduce the amount of power dissipated. So I chose to use this power MOSFET, which has a drain to source voltage of 100 volts. It's quite a lot of voltage and can sustain current of 4 amps. So in order to try to get as much gain out of this as I could, I used this Zener diode to resistor and ground combination. Basically, this Zener diode kind of acts like a voltage-controlled capacitor, so it starts to build up charge as it sees a voltage across it, and then as the amplifier, or as the input signal goes into the amplifier, it starts conducting, but then as the input signal drops off, it automatically shuts off, so don't have to add any extra switching for that. Then we just developed some of these RF switches where we could just turn whole sections of the transceiver system on and off. This control voltage here comes off is connected to the microcontroller, so that when a 5-volt signal comes in, it turns the signal on. If it's low, it breaks the signal. So before I put this all on a single PCB, I wanted to be able to actually take individual chunks and make sure that these circuits were working. So I built them on tiny little modules. I'd put them in the simulator first, come up with a full design, and then take that simulator onto a module and test it. So here's the schematic of the local oscillator and the output, which is right at about 7 megahertz. This was a second harmonic, but it's really far down at 14 megahertz, so we don't have to worry about that very much. This was the actual module build where I constructed it on this little piece of copper laminate just kind of in the air. All these inductors are just hand wound to get the value of inductance that I needed out of them. So it's kind of like sewing these little things together. Overall, the simulated versus measured was pretty spot on. As kind of predicted, simulations tend to look a lot better than measured performance when you get all these parasitic capacitances and wires in there. The tuning range, we got actually 42 kilohertz of tuning range, which is quite a lot considering that in earlier attempts without using these external tuning elements, I only got about 1 kilohertz. So that seemed to do pretty good. And then some really nice incremental tuning. Here's the schematic for the single tuned low noise amplifier. Added a second transistor to match the output stage at 50 ohms. This is how the simulation looked. We get these S parameters. Basically, the orange line is the gain of the amplifier. So how much gain are you getting between the input and the output? While S11 is the amount of signal that actually gets reflected out of the amplifier. So here in the blue section, the more negative, the better. And in the orange, the more positive, the better. So mainly it was this right here where we saw between 7 megahertz to 7.1, the amplifier was getting really good gain. So it's about 40 dB, which is quite a lot. It's about 10,000 times the amplification. When we built it, I did the same thing on a VNA, took these measurements, and they look surprisingly similar considering how ugly that module is. But there was a little bit of a difference, was that the maximum gain shifted down by about 300 kilohertz. So I had to go back and retune this inductor here due to that. It was a little too large, and so it was moving the frequency, the peak frequency back. Here is the simulated circuit of the audio amplifier. 1 op amp followed by another op amp, and these 2 transistors delivering power to the speaker. Overall, was able to get 90 milliwatts into an earbud. So 32 ohm load, that's enough to exceed the threshold of pain. So I would say that it amplifies just fine for a few components. On the right here, we have figure 4.12, which is simulated versus measured frequency response. So pretty similar. There was a little bit of reduction here due to a different cap value, but nothing to write home about. Then I built the transmitter. I did not actually build a module for the transmitter. I just developed it kind of as I brought up the board. So here's the schematic for that. This schematic actually includes both the driver, the final stage, and the low pass filter that would be connected to the antenna. So simulated versus measured came in very close. As usual, simulated looks a lot better, more efficiency, higher power, but 34.7 dBm is about 3 watts. So that's a good amount of power. And from this graph, figure 5.2, this is all on a 12-volt system. So what amazes me is that doing this, you wind up getting 17 to 20 volts out of RF out of the amplifier, and it's always kind of amazing to me where does that voltage come from? But the inductors provide this voltage for us, so it's able to function at the levels we want. This is just a quick shot of the digital RF switching circuitry. This is the microcontroller, the AT-Tiny, all its pins that it's connected to. And this is kind of the package that it comes in that we can use on the printed circuit board. This switch 1 represents the key, so as I key down the transmitter, this takes the instruction and sends all the control voltages to the separate parts of the system. This is the LT Spice schematic of the RF JFET switch. So this is how we simulated the voltage from the microcontroller. And I simulated the turn on time. So how long does it take this switch to actually open up? And in my measurements, I got about 14.8 millisecond or microseconds. So that's 14.8 millionths of a second, which is about twice as high as the simulation recorded. So again, very expected. Simulations are rather optimistic, but really tiny amount of DC current. So that switch is hardly dissipating any power, which is perfect. We don't want our switches to dissipate power because it wastes their battery life. We're trying to run it on a battery. So then I had to integrate all these systems now. So this is the final schematic for the last revision, where we have every part of that block diagram represented here from input to output. So the antenna jack is actually right here, and this is the audio jack. Did some field testing on the Oregon coast with the receiver there. That was pretty fun. And then did this PCB layout for the circuit board in EagleCAD. You can do these. EagleCAD's a free software. You can make your own layouts and then send them off to Osh Park to get this produced at their fab house. So then we did all the assembly there, mounted it in this nice aluminum enclosure, and then did some over-the-air testing. So this is pretty cool because here I was transmitting on 7.038 in Portland, and then I took the screenshot of an actual receiver that's in Corrine, Utah, that I can look at what signals it's receiving out there. So they're about 500 miles away, and this is my little 3-watt signal coming in on their receiver. Additionally, there is also a website called Reverse Beacon Network, where several computers are just scanning certain bands, looking for Morse code stations calling CQ. And these are all entries where I was logged. These stations here are in central Canada, so they're about 500 to 800 miles. This was in Nevada, and this was about central California here. So they let you know how far above the noise you're coming in, and what speed was your Morse code. Really cool way to test whether or not I'm able to get out. And this is just kind of one of my favorite graphs of the recordings I made from the audio receiver. This is a logarithmic audio spectrograph. And on the left here, I didn't have any of these audio filters in. So down here, you can see N5AW in Marshall, Texas saying, "Thank you, Bob." And then these are all the stations just coming in on top of them, very loud. Sometimes 4 kilohertz, almost as loud as the station I'm trying to listen to. Over here, you can't even see the noise above 3 kilohertz here. It's totally silent. So this is the actual radio noise, the static, and then a really loud station coming in right about 516 hertz. So, I think this is a great way to kind of visualize what you're actually listening to when you're listening to a direct conversion receiver. So in the future, I think I would like to add some more frequency agility, give me a little more tuning range. Fortunately, it's kind of limited still. Also minimizing the clicks and pops on the audio output. Some are quite loud, so it'd be nice to kind of attenuate those and see if there's a way to not have those be as prominent. Digitally controlling the incremented tuning, I think, would be interesting from like a digital mode standpoint. You could really take advantage of these things called Whisper, PSK31, these other digital modes that exist out there on these frequencies. And automatic gain control, maybe some image rejection so that we're not listening to 2 sides of the local oscillator at the same time. But that is the transceiver in a nutshell. And if there are any questions, feel free to let me know.